supervisor Michael Wolf. So if we consider a multipartite quantum system of spins in a one-dimensional chain, such that to each spin I assign the Hilbert space CD, I want to study the set of density operators that remains once I trace out everything from my system but the neighboring spins, like in the picture here. And even more, I want these density operators to be translation invariant in my quantum spin chain. So this set I denote by red D, red indicating reduced density operators, and D indicating the local dimension of the Hilbert space CD. Just to have an intuition more geometrically, so this red D is just a convex and compact subset of the set of all 2 QD density operators, which is also a convex set in itself. So in principle, is a set easy to define, but otherwise difficult to characterize. What are we using also in our work is we consider only nearest neighbor interacting Hamiltonians, which I denote by H. And the total Hamiltonian of my system is just going to be the sum of HI plus 1, so spin I and spin I plus 1, so that the Hamiltonian acts non-trivially only in these spins, I and I plus 1, and everywhere else as identity. So it is well known that the ground state energy density in the thermodynamic limit can be calculated by just taking the limit of the number of particles going to infinity and taking the infimum over all n-partite density operators here, and the trace of my n-partite density operator and the overall Hamiltonian, which is just the sum of the small HI plus 1. We can simplify this formula further because we're only considering nearest neighbor interacting Hamiltonians, and this becomes this minimization of the trace, where rho is just a density operator, translation invariant, bipartite, and H is the Hermitian operator that characterizes my Hamiltonian. So in principle, if we could say something about how red D looks like, we would be dealing with a convex optimization problem of a linear functional, which is trace, and red D is convex, as I said. So if we could characterize, so if we would know how red D looks like, then we could say something about the ground state energy density. So in principle, it is rather important set to calculate the ground state properties of quantum many-body systems. And the question we ask is whether red D has a finite description, so a finite explicit description. Just to get some intuition how the set looks like, I take the local dimension to be 2. So here I'm considering systems of qubits, and H, so the Hermitian matrix is going to be just in C2 and C2, so a 4x4 matrix. And the family of translation invariant Hamiltonians, by a priori assuming that I'm setting the lowest energy to 0, is going to be a 15-dimensional family. And similarly, red 2, so 2, again, indicating the local dimension, so qubits, is just a subset of the set of all bipartite density operators, and again, is a 15-dimensional convex and compact set. So in principle, it sounds like a simple set, but why is it so difficult to characterize it? What have been known and studied in the past has been approximations from within and also outside, but I'm going to talk only from within here, for the set red D. So if we consider matrix product states, then increasing the bond dimension of the matrix product state, we get a better and better approximation of the set red D. But this again involves a limit of infinite many variables, but exactly about the set red D, we don't know anything. So what we showed is that in dimensions 2 or higher, the set of reduced states cannot be described by only using finitely many polynomial equalities and inequalities. If we could have done this, it would have been very nice because we could have determined the ground state energy density, but we show that this is impossible. And before I show you how we prove this main result, I want to introduce you to the toolbox, which basically in its heart is just separating transcendental structures in one side and algebraic structures in the other. So just a brief review. I think we all of us know what an algebraic number is. So all the numbers which are roots of non-zero polynomials with rational coefficients, we will call rationals. And the typical examples, the set of rationals, integers, the golden ratio, and many more. And if a number cannot be written as a root of some non-zero polynomial with rational coefficients, then the number is called transcendental. And almost all complex numbers are actually transcendental. Here I just wrote the two most famous examples, e and pi. And even though we know that both e and pi are transcendental, we actually don't know whether their sum or product is a transcendental number. I wrote this here just to highlight how difficult it is actually to show that something is transcendental. This separation between algebraic and transcendental numbers can be uplifted also for functions. So we will call a function algebraic if we can write its graph as the polynomial as some polynomial relation. And the typical examples, again, by definition, all polynomials, all algebraic functions, rationals. And if we do not have such a polynomial relation for our function, then we will call the function transcendental. And again, the usual suspect, the exponential, the logarithm. And this separation can also be done for sets. So we will call a subset A of a real vector space semi-algebraic if we can write this set using only finitely many polynomial equalities and inequalities. So I wrote this star here just to indicate that I can use either inequalities or the equality. And just to get a sense, for example, if you are in the real line and we have a singlet, then this is going to be a semi-algebraic set because I have the polynomial x minus a, which characterizes my set. So even more, this is actually algebraic, and semi comes just from the fact that I can use inequalities. So by definition, every algebraic set is also semi-algebraic. Also intervals, because I can write this as a polynomial inequality with the polynomial being b minus x. And finite unions, intersections of semi-algebraic sets will be semi-algebraic. And if I do not have such a representation for my set, then the set will be called transcendental. I wanted to mention that because most parts of quantum information theory is defined in finite dimensional vector spaces, we can find semi-algebraic sets almost everywhere in quantum information theory. And the one example I wanted to mention is the set of density matrices. Why so? Because we want our matrix to be positive semi-definite, and this is if and only if my matrix is Hermitian, which gives rise to a polynomial, and all principal minors should be non-negative. Of course, here the real vector space that I'm working with is a set of complex Hermitian matrices over R. And also I need to normalize a trace, which gives rise to another polynomial equality. And of course, since I'm having only finitely many of those, the set is going to be semi-algebraic. As I mentioned before, semi-algebraic sets have many interesting and powerful properties that we need in quantum information theory. And probably the most important one is Tarski-Seidenberg theorem. I wrote here the most simple version, but I can simplify this further, so we don't need to remember this. And we can only remember that if we have a semi-algebraic set and we take quantifiers over sets that are themselves semi-algebraic, then this keeps us in the semi-algebraic world. And this is a property which doesn't hold, for example, for algebraic sets. And I mention this because this is also going to be one of the main theorems that we use to show that red D cannot be written only using finitely many polynomials. There are traces of semi-algebraic geometry and transcendental number theory in the quantum world, and people have used these tools to study undecidability problems, to study circuit complexity, to study the existence of certain finely correlated states, and also to study properties of entropy functionals and their relation to the impossibility of single-letter formulas. OK, so let me now mention one of the main motivations also why we wanted to study this set. So in the paper of 92 from Fanes, Natagalia, and Werner, they used the separation between algebraic numbers and transcendental numbers to show that the ground state of the n-spin 1/2 antiferromagnetic Heisenberg model cannot be a finely correlated states. So finely correlated states are translation invariant states that have an algebraic structure, so you do not need transcendental methods to build them up. So if we consider, say, a ring with n qubits, and we want to evaluate the ground state energy, then as long as the number of particles is finite, this is going to be an algebraic number. So this here, q bar, denotes the field of algebraic numbers. But when you take the number of particles to infinity, then the number becomes transcendental. Therefore, the antiferromagnetic Heisenberg model is just a point in the red D set. And it's a transcendental point. But this is not sufficient to say that the set itself is actually transcendental. Therefore, we need to introduce some new methods to further study this set. OK, so by now, we all understood that the set red D is not semi-algebraic. And how we show this is by contradiction. So we assume that this set is semi-algebraic, and we want to see the implications that we get from there. OK, so let's assume that the set red D is semi-algebraic. Then I want to consider a map from an interval I in R to H gamma, where H gamma is going to be in the set of Hermitian matrices, such that each entry of this matrix is a polynomial function. And this H gamma is going to be just the family of Hamiltonians, basically. So you remember I mentioned this H as the nearest neighbor interacting. And now it's going to depend on gamma. So we have a family of Hamiltonians. And since we have this dependence of H in gamma, then of course also our ground state energy density function depends on gamma. So before I mentioned what an algebraic function is, but we will also need what a semi-algebraic function is. So if we know that the graph of a function is a semi-algebraic set, then the function is going to be semi-algebraic. So this is what we do here. So we study the graph of the ground state energy density. So what is this? This is the set of E and gamma, where E is some energy, and gamma is in the interval I. And there is going to exist a state from our set red D so that we achieve the minimum energy, and every other state is going to be at least or equal, is going to be greater or equal than E. So now let's analyze the graph. So this part here is a polynomial. This part here is polynomial equality, and this one here is polynomial inequality. This can be R+, and I mentioned at the beginning that intervals in R are semi-algebraic sets, and the same for I. And here we are having quantifiers over set red D, which we assume that it was semi-algebraic. So therefore, because I'm having red D semi-algebraic, H gamma is a polynomial function, and I'm taking also quantifiers over semi-algebraic sets, then this makes my set semi-algebraic by just applying Tarski-Seidenberg theorem. What does this mean? Well, this means that the ground state energy density is itself a semi-algebraic function. And all what it's left to do is to find a model that fulfills the fact that H gamma is a polynomial, but its ground state energy density is going to be a transcendental function. And one example of such model is the XY model, where H gamma is just this expression here. These are the Pauli matrices, and we all agree that when we tensorize these and we multiply with 1 minus gamma and 1 plus gamma, this gives a matrix so that each entry is just a polynomial function. And it can be shown that in the thermodynamic limit, the ground state energy density of this model is a transcendental function. We use this fact to show that for dimensions 2 and higher, the set red D is not semi-algebraic over R. What does this mean? Well, this means that no semi-algebraic ansatz, even if we allow for transcendental parameters, can describe the set of reduced density operators exactly without having to involve a limit of infinitely many variables. But a natural question to ask is, OK, so I want to not only use polynomials, but what happens if I allow to use some transcendental functions? We also studied this question, And okay, let's say that we want to use some transcendental ingredients and we want to allow the use of the exponential. Because we allow the exponential, implicitly we also allow the logarithm. And now we are working over the field of real numbers, but we expand it with the use of the exponential function. And because of this very powerful result, which says that the ground state energy density problem is not decidable, we get the following dichotomy. So either the set red D is not definable in the first order language of the RXP. What does this mean? Well, this means that I cannot write the set red D as a Boolean combination of finitely many polynomial equalities and inequalities, and also using the exponential function. So either this is true, or Shanwell's conjecture, which is the most powerful conjecture in transcendental number theory, is false. So Shanwell's conjecture basically says that if you have n complex numbers that are linearly independent over the field of rational numbers, if you expand this set with taking their exponentials, then this set is going to contain at least n algebraically independent numbers. Algebraically independent, it just means that there is no non-zero polynomial over the field of real numbers such that it has these numbers as 0. But I don't expect anyone to remember this, but just to highlight how important this conjecture is, in the beginning I mentioned that even though we know that both E and pi are transcendental, we don't know what their sum or product is. So if Shanwell's conjecture is valid, then this would imply that both the sum of the product of E and pi is going to be transcendental. So my hope, and I think of many people, is that Shanwell's conjecture is true. And with this, I want to end my talk, and I want to thank you all for your attention.
Thank you for the nice talk. It means that you cannot describe the set of density matrices, reduced density matrices, as an algebraic set. Mm-hmm. But can you say something about how well you can possibly approximate it? I guess no.
No.
Okay, but I mean, in principle, what are your thoughts on this? Like, how would you approach something like this?
I mean, the approximation is this work that was done by Sirac and Verstraete when they approximate. So the best known example is this approximation with MPS with increasing bond dimension. But there is nothing else that is known about this. And all these approximations for fixed dimensions, they're all semi-algebraic. But when you go to the set itself, then it becomes transcendental.
Thank you very much. I don't know. Does it work? Yes.
Yes.
Why is the ground state energy in this XY model transcendental? It's a bit surprising, no?
It is actually, so people have studied exactly how the ground state energy density looks like, and it is something that is called a complete elliptic integral of the second kind. And there are some characterization of these functions, and it's known to be transcendental. Just people didn't put the facts together to show that it's actually transcendental. But yeah.
Is there many things that are transcendental in this, like many models where we know this, or is
this is the only one I studied. I wanted to study, yeah, maybe potentially, but this is the only one. I needed just one counterexample to finish my proof.
Yeah, thank you.
Hi, yeah, thanks for the nice talk. I was wondering, so the XY model you've defined here you're defining it over qubit. Like you have some qubit chain, yes?
Yeah.
Maybe I missed it, but so you'd only need a qubit counterexample in some sense to prove?
So we show it for 2 dimensions, but this holds also for higher dimension by just embedding Hilbert spaces to higher Hilbert spaces.
I see, okay.
Yeah. There's a question there.
Thanks for the nice talk. So you mentioned this approximation of ground state using MPS. Mm-hmm. So I think there are actually people try to connect this precision of approximation with how much Rayleigh entropy you have in your system. I just wonder whether your result implies something about this Rayleigh entropy.
I didn't know about that.
Thanks.
So I don't think I can say anything about it. Okay. But we can talk about this later. Sounds interesting.
Yeah, thanks. Yeah.
Hi, thanks for the talk. So I wonder, like, have you considered higher dimensional spin trains, and what would be the result there?
So we proved it for dimension 2, but it holds also for higher dimensions.
Oh, I mean, not the local dimension, like the
Yeah.
dimension of the lattice.
I mean, here we consider only the infinite spin chain, but the only thing that we work with is basically the local dimension, so it should hold also for any higher dimension, basically. Yeah.
Maybe just that question.
Mhm.
So you would just, for example, if you just take XY chains, a collection of XY chains, the grounds, you just need a 2D model that has this semi-algebraic ground state energy. Basically, that's all you need, right? You need a model where you can show that the ground
So
state
the
energy
proof,
graph is
yeah, the proof how we show it, like it's for any, doesn't have to be for qubits, so it's for dimension D. But in order to find the counterexample, we just needed one model, no matter which dimension.
So
shows.
you could, for 2D, you could just take a collection of chains. Would that be good enough? All right. You asked one.
Sorry, just a small comment, but for 2D, my collaborators and I, like more than 10 years ago, proved that classical distributions in 2D that are translation invariant, if you take like, this is already not semi-algebraic.
Yeah, very good point. I put up a slide in the end.
Put everything but my paper.
To show that to show that the classical case for the lowest dimension is actually semi-algebraic. But when you go to higher dimensions, it becomes non-semi-algebraic, apparently. Yeah. This is due to frustrations. But yeah, this is the only quality that we need to characterize classical translation invariant spin chains. And this is very semi-algebraic, even algebraic.